Welcome to The Machine, a podcast from Waterford Institute of Technology. My name is Rob O'Connor. I'm a lecturer in the Department of Computing and Mathematics at WIT, and I'm joined by three of my colleagues today. We have Mairead Meagher, Siobhan, Drohan and Eamonn de Leastar, all of us in the department. I want to talk about computer programming today, just what is it, and maybe try to make a little sense of it and remove some of the mystery. The Wikipedia definition: computer programming is the process of designing and building an executable computer program for accomplishing a specific computing task. That's quite opaque. Mairead, could you maybe put a bit of flesh on that, please?
I'll try, Rob. If we look at an algorithm first, what we want to do is we want to tell the computer exactly what to do, a set of steps in order to achieve some result. So it could be to calculate the area of a square. It could be to send off missile into space. Probably just we'll start with the square. So it's just to think about if you met somebody that just came down from Mars, how would you explain to them how to do something using a very simple set of steps? Because you'd have to tell them how to do that in a way that they would understand and that they couldn't get mixed up on. So the computer is this Martian. So you have to think about the computer as being explained this process in this set of unambiguous steps. And if you think about it like that, how are we going to do that? We need to think about how we're going to solve the problems. And if you think about something like going to a bank machine, you do the same thing every time. It's a set of steps. You shampoo your hair every morning. Maybe not every morning, Rob. I don't know how you do that. But you do the same thing every morning. So you know what you do. You make decisions in the middle of it that you either go one way or another. You do certain things over and over again. And in fact, everything I've said there, that's all you need in programming. You need sequence, you need to be able to decide things, and you need to be able to loop. That's all you need. Then once we've done that, we need to decide what language we're going to use to make that accessible to the machine. And that's what we call the programming languages. So
if I can stop you there, because you've introduced an awful lot of concepts there that are very relevant to computer programming, but you've introduced a word called algorithm. Mm-hmm. And that's something we'll hear an awful lot. So Siobhan, perhaps you might maybe describe just what an algorithm is.
So an algorithm is basically, when you do start to program, an algorithm is the plan of attack that you're going to have for solving a problem. So Mairead said things like going to the bank machine. So within that computer program that the bank would have written, there would be an algorithm for how you would take your money out of the machine. When you think about how do you take your money out, you put your card in, you put your PIN in, it's read. They check whether you have your enough balance. You decide how much you're taking out. Do you have the right balance? All of that is an algorithm of how you are allowed to take money out of the machine. And somebody would have had to sit down and figure out all of those individual steps and come up with the computer program around that, which is when the computer languages start coming in. You decide what language is best suited for the particular scenario that you're coding.
So it's essentially, a program is a very detailed description of a sequence of events.
Exactly. Yep.
Okay.
That's it.
Now, we've touched on computer languages. Computer languages often have very opaque names like C or C++, Java, Perl. There's heaps of them. Newer ones have kind of sexy names like Kotlin and Swift that sound very fast and zippy. But when we talk about computer languages, is it like learning French? So I might give this question to Eamonn. Is it like learning French? Is it like learning Japanese?
Not quite. It's more much simpler than that, in fact. Generally, we're dealing with a very restricted vocabulary, very small number of words. We do have words in them that are often English, but the total number of words might be 30 or 40, not hundreds. It's more about the sequence in which we assemble the words and the structure around which we place the words. We're often using non-literal symbols like brackets and dots and hyphens and punctuation of various kinds. When you look at it first time, it looks quite alien. But we find the students in the first few weeks or so very quickly get to grips with what they're dealing with. It's not quite like mathematics. It's a bit more free-flowing than that. A bit more room for creativity in how you put together the program, if we call it that, than, say, solving a problem by composing a proof of some kind or a derivation. But the language itself is, they're all quite similar to a certain extent in different families. And the fundamentals of the language are usually the first thing you grasp. It's how you compose in the language that's much more challenging.
So is that essentially code? When we talk about computer code, this is some sort of syntax written in C.
Yeah. Code is just shorthand word for a program.
And the same with, there's other terms like software development. That's another term.
Yeah, that would be the process of building it.
Yeah.
And then we talk about modules and components and all this paraphernalia, which are other ways of describing how code is packaged up.
Do you ever wonder that perhaps the language around computer programming, even terms that we've talked about now, is maybe one of the reasons why people find it a little bit difficult to get into, that there's a whole vocabulary there that is a bit alien? I don't know, Siobhan, what do you think of that?
Oh, there's definitely a lot of jargon out there. But a lot of the jargon that is there, say like we have words like encapsulation, and it sounds absolutely what does that mean? But all it means is you're just hiding your data. So it's just a matter of learning some of those terms and demystifying those terms, which are actually simple enough concepts underneath the hood when you move past the jargon. But you'd be surprised how fast you pick up the jargon. Within one semester of programming, you would have a huge amount of technical jargon. And underneath them, the concepts underneath those some of them are very simple.
Eamonn, you touched on something there that we might just explore for a moment. And you talked about mathematics and designing a proof in mathematics, but we often hear about the relationship between computing and computer programming and maths. So how does that manifest itself, or is it even relevant today?
There's some relationship, I think, in terms of your own interests and your own way of thinking between maths and computer programming. But knowledge of a specific range of mathematical concepts, or even a great competence in them, isn't absolutely essential. Programming tends to be more about logical thought, and then applying that logical thought to approaching, as Siobhan was saying, a sequence of steps to solve a problem. But in maths, there might be a limited number of ways in which you might proceed. In programming, it's wildly variable. So we would say it's quite creative potential is quite significant.
Would you agree with that, Siobhan?
There's one thing that I noticed that we do use from the mathematical side in programming would be at the very first when we start teaching programming, we would use things like order of precedence. If anyone remembers their maths, they would have done things like BOMDAS and at
brackets.
a rude, brackets, multiplication, division, or some other people say to me they learned it as my dear Aunt Sally, multiplication, division, and it's the addition, subtraction. It's the order that the computer processes things. So at a really rudimentary level, we do use maths, but as Eamonn was saying, you can use. It depends on what you're building as to what level of maths you're going to be using. Like if you're building games, you're going to be using a lot of kind of geometry stuff, positioning stuff on screens, using your X and Y points, things like that. So maths does come in on many different levels, but it depends what you're building program-wise and what final project you're going to have as to what level of maths you will be using.
Okay, so computer programming has been around for a significant period of time, since arguably 1940s. Okay, you can say it comes before with Ada Lovelace, but computer programming, how has it evolved since, say, the modern computer age of the 1940s to today?
Yeah, it's an interesting point. One of the first languages was Lisp, which is 1940s, coming out of efforts in the Second World War. Next programming language after that in the 50s was Fortran. And we discuss this with our students occasionally. Those two languages are the ancestors of all languages. So you could draw a little family tree, if you like, of programming languages, a bit like a rock and roll family tree. Fleetwood Mac are related to everybody. Those two languages turn up everywhere. One of them still lives, in that you can still program in Lisp 50 years later. Other languages from that era are gone, but their descendants are easily recognized. But if we look at a language like C or Java, those languages stabilized their concepts in the 70s. So You pick up your phone today and it's programmed in C++ or C or Swift or one of these languages. They would be instantly recognizable by anybody programming in 1975.
So Siobhan, why are there so many computer programming languages then, if they're all the same?
Well, one thing that you'll notice is that new languages emerge as a reaction to something that's missing in a previous language. So C would have had a lot of kind of scary syntax and stuff like that. So C++ would have emerged, and the syntax then in C++ wasn't exactly what we wanted. So next thing, Java would emerge. So different languages will emerge based on a reaction to one older language not fulfilling everything that's needed by modern technology development.
And Mairead, you wanted to jump in there, did you?
Yeah, it's about the maths and why people sometimes feel that maths and programming are connected. And again, I'd reiterate Eamon's point. It's not that you really liked a bit of calculus or particularly stats or something like that. Is that if you got a maths problem that you liked getting it out and you liked that process of working at something and the buzz you got when you got it out, or a puzzle or something like that. And that buzz, that's what we're going for. That's what keeps you going when you're trying to work out a program, and it's the same energy that you'll get from that. And just think of the night, the time that you got that puzzle out, or you got the maths problem out, or whatever, and how that made you feel. And that's what programming gives you, and that's why it's so exciting.
There's a famous urban legend about World War II in Britain, and the Times crossword. If they used to do these periodic crosswords. And if you could solve this crossword, you know, these cryptic crosswords, and if you could solve it, you come down to the office and you're going to win a prize, and you come down to get your prize, and they'd say, "Oh, can you solve the crossword?" You say, "Oh, great, congratulations, you've just been drafted to Bletchley Park." That because they were looking for people who liked puzzles and stuff, and that's where a lot of the birth of the modern computer has kind of come from that.
Can I just say to somebody who's just started trying to learn how to do cryptic crosswords, you don't have to know how to do cryptic crosswords to do programming. All right?
Yeah, it's also, I think solving puzzles is part of it, but also building something. We often talk about building an application. And there are kind of analogies that have been used to engineering, to architecture over the years, to Lego, for instance. Building medium-sized programs a lot of it is about fabricating pieces. These are all in your head now and in code, and then putting them together over time in multiple layers. So it's quite fun, really. And it reaches a different part of the brain than necessarily understanding of, as Mairead was saying, of calculus or differential equations.
So we've talked about the syntax, and the syntax and languages have evolved over the years. One thing that has certainly evolved, and I can see it in my short time in this game, is the tools. And when I talk about the tools are the software tools that we use to actually write code. So they're the editors, the compilers, the builders. I mean, how have those evolved over the years?
They've become more visual, and they've become more sophisticated than we would have had 10, 20 years ago. Many of the same concepts are still in there, and there's usually more than one way of doing the same thing. So you can pick a very fancy tool that has got a lot of graphical elements and have great fun with it. You might find your neighbour is using a completely different tool and getting the same results. So it's not quite that the tools have all converged on one way of doing things. We just have a huge variety of tools now.
And are they so could you give us an example of some of the tools that you would use maybe teaching programming in the 90s, say pre-web, and some of the tools teaching programming 2018? Mairead, maybe what you do with the first years.
Well,
so I suppose we should establish that yourself and Siobhan teach programming fundamentals 1 to first years who have never done any programming before.
Yes.
You assume that you haven't done any programming before.
We always assume that, and we always will, really.
Yeah.
So really in the 80s we'd have had a very simple editor, really, really simple, with very small number of controls. So like a notepad, a kind of a text editor. Absolutely, text editor. And you would submit that with 3 little commands, and you'd go away and you'd have your coffee for 20 to 30 minutes while it compiled, and you'd come back and you'd say a little prayer on the way back that it worked, because it'd take another 30 minutes to check it again.
Yeah.
And you go from that to now where you press your button, you see whether it works or not immediately, more or less. And it helps you to know, it helps you why it didn't work, or gives you tools to help you to do that as well.
So you introduced a word there, compiling.
Yes.
What's the process of compiling?
So Eamonn mentioned earlier that the code that we write in, like C or Java or any of those, they're what we call high levels. So even though they look a little bit magical when you read them, there are English words in there. So that's why we call them high level code. But the computer only understands ones and zeros. So we need some mechanism to get it from that wordy set of steps to the ones and zero, and this is what we call a compiler. So that is the now, if everything isn't perfect in the code that you've written, it won't get through to the ones and zeros, and that is the process that sometimes you have to do over and over again.
So could you give us an example then of the actual names of some of the tools that you would use today? Siobhan, like what tools do you use today with the first years?
With first year programming, what we do is we actually use an artist tool. There's a tool called processing, and if you go to processing.org, you'll see it there. And what it is you can program in that in Java, JavaScript, Python, a lot of languages. And we decide to use Java because it's a real core software development language. And what processing does for you is it allows you to draw loads of different shapes and have animations, and kind of as you move your mouse around a screen, that circles will follow it and circles will change colour. So we use kind of an artist tool to teach the fundamentals of programming at the beginning. So we use that for about one semester, and then you get a really solid grounding in the basics of coding in a very visual way, and it's really cool. It's by the end of the semester, students are building games like Space Invaders and Frogger. If anyone remembers all these arcade games, they Google a lot of arcade games and they go and they build them in Java, and it's a real visual way. And then what we do in semester 2, we move into what we call proper software development. So we choose one of the new tools that are out there for that are used in industry for actually developing proper software. And we generally have something like Eclipse or IntelliJ, and they're huge tools, and we use a little subset of the functionality in there and start students building all of their proper banking software, whatever software it is you're building.
So we've talked about syntax, we've talked about tools. Now there's another term that I've heard bandied around over the last couple of years. I'm not entirely sure what it means. So it's DevOps, or developer operations. Is this just another flash in the pan buzzword, Eamonn, or is there something to this? What does it mean?
It's just the latest name for something that's always been there, really. But it's probably become more important in the last 4 to 5 years, particularly with the notion of the cloud, whereby we imagine we're writing our programs. They're not necessarily running on our phones or on our computers. They're running somewhere in the cloud, delivering a web service or delivering some intelligence. If you go back to the tools for a moment, it's all of them, no matter how sophisticated, have a simple enough idea. You're writing down the code into a text file, you press a button and it executes. When you press the button and it executes, it'll only run if there's no errors, and if it's running, you'll see something. You'll see some sort of activity. DevOps is a term that is perhaps not so much around writing the program, but what happens after the button is pressed. For a simple application, there's no DevOps because you're just running it on your tool. But if the code you've written is more sophisticated, if it's got to be bundled up into a mobile app, deployed onto a Play Store or the Apple App Store, or got to go on to Amazon and live in a society of other programs that are running in the cloud, then all of that stuff is DevOps. It's not really programming, it's kind of organizing the program after it's written.
So would it be that it's not just that the program is working, it's that it's working well and working well with others?
Yes, and it isn't failing. And maybe if it does fail, what happens? Maybe start it again. And then maybe you want to upgrade it. How do you do that? Maybe can you upgrade it and replace it without it impacting on customers, for instance? All of that is in the world of DevOps. Oh, sorry, the big one in DevOps is scaling. I sent it, and it's being used by 100 users, and now there's 10,000 want to use it the next day. That's not really programming, that's DevOps.
Right, okay. So it's like, I suppose I'm trying to think of an analogy that somebody might, it's like if you're trying to cook something at home.
Absolutely.
Cooking for 4 people is not too bad. Cooking
Yeah.
for 40 people, it's the same process, but the complexity is exponentially greater.
Yes, and I suppose you might be looking at systemizing the cooking and kind of routine for caterers getting involved, this kind of stuff. That would be scaling up.
There's a side aspect to this that we might explore just for a moment, and I think it's quite interesting that in the room here there's 4 of us, 2 male, 2 female, but that would not be representative of the computer industry in 2018. So maybe Siobhan or Mairead, one of you might take this. There's a gender imbalance in computing.
Absolutely.
So one, I don't think there's any biological reason for that. But why is that the case? And maybe what can we do about it?
Interestingly, there's no solid research reason coming out. So there's nothing we can be absolutely sure of. There's a few things we think it might be. I think myself, anecdotally, I think girls seem to think that if they're not addicted to games or if they don't really like playing games, that computing isn't for them. And I mean, obviously to us that seems like it's so far off what they're going to be doing here.
But is that maybe because games are probably the most visible
that's exactly
aspect
it.
of computing?
That's exactly it. And I think people liking games is so completely separate from people liking writing programs.
Yes.
But people don't make that link. And to me, it's so tragic almost, you know, that there's so many wonderful women out there that would be fantastic at this and bring, you know, so many dimensions. And we've had some fantastic female students. We've had some fantastic male students, of course, as well. But like female students that get so much out of it. And like, I suppose I can speak for myself. I've had such a wonderful career from starting out and doing programming, being in computer science. I mean, I you know, it's been just wonderful to me, and it does, you know, it gives you so much scope and so on. But the point is, every woman out there, you know, 50% of my class when I was in college were female, and it's just gone away from that for no good reasons. The same skills are needed: problem solving, looking at things, wanting to get things working, being buzzed up about that, and all your other skills will come into that, wherever they are, male or female. But it's not just male, and you know, just give it a go. Think about it. Do not let anyone tell you that it's not for you because you're a girl. That is like archaic thinking, and it's become more reasonable to say that now, which is very strange to me.
I worked briefly for IBM and in a team working on insurance software, which was very sexy. But there was one of the girls working on the team, and she was one of the best programmers I ever met. But she hadn't trained as a programmer. She was originally an archaeologist. And somewhere along the way, she had decided to jump into computer science. And I wonder, maybe was it something to do with, you know, archaeologists are very methodical in the way that it's not Indiana Jones running, jumping and, you know, dodging bullets. They're very methodical in the way that they approach a dig site. And I wonder perhaps maybe that was one of the reasons why she was good at programming.
Yeah.
You know, she was just methodical.
Yeah, there's so many different skills that come into it. But please don't switch off because somebody said women don't do it.
Yeah.
I mean, that wouldn't be allowed in the Middle Ages. I mean, that's Middle Ages talk. Like. And people are accepting it now.
Yeah, I know we're laughing, but we shouldn't.
No, it's
and of course, you remember it wasn't always the case. The 90s here was
absolutely
half
not,
and half.
half and half.
We'd have regularly have more women in classes than
absolutely.
men. But I think the games that they might be, they became very pervasive around the late 90s, early 90s.
And that was when
that's when things shifted a little bit.
You know?
And is
It's
that to
not
do with
the same thing,
a lot of the games that are kind of the big hitter games are very action, conflict, male-oriented, shoot, you know, win World War II all by yourself kind of thing.
Seriously. And to say we're not looking to attract people that really love to play games 24 hours a day would be quite true.
Yes.
Right? That's not the market we're going for, right?
Yeah.
We're going for people that actually want to solve problems.
Yeah.
Yeah.
Right. So finally, this is a kind of a strange question, but we might get your thoughts from the three of you on it. Is computer programming hard?
It all depends on what you're doing. Mostly, I've programmed for years. I've worked in industry for years and taught here, and I've never found anything too hard to do. The most of the programming that you will go out and you'll do in industry, it's a challenge, but it's not hard by any means. And it's a case of just learning. Once you know how to do the basics, you can build anything. So I presume if you're putting a rocket, I've never actually coded any of this stuff, but if you're putting a rocket into space, I'm sure the coding in that is far more complex than what you would generally do in a normal organisation. But the answer is, once you know your basics, you can build anything.
I would think that if you're suited to things, it's not as hard. So I really wouldn't like to be attacking a French literature, a literary novel, and trying to do analysis on it. That would be hard for me. So it depends on what your skills are. So nothing is hard if you're motivated enough for it. It's not that hard. It's actually really exciting.
Eamonn?
Sometimes it's useful to think of it as not so much a science as a craft, and a craft that you learn over time at your own pace, and that you never stop learning. So when you start it initially, sometimes we find students can't make any sense of it for a while. But then once they find a groove, once they relate to it in terms of their own intellectual ways of thinking, they can be amazingly good over time, proceeding up the ladder in the classes themselves to be maybe the best students by the end. But take your time initially. The idea of a craft is that you often have to use different sort of senses when you're putting together a program. It's not just mathematical, methodical. It's also a sense of elegance and kind of beauty about an algorithm that's coded well. That takes many years. And one of the beauties about the industry is it's something you never stop learning. Yeah.
I think that's probably a nice place to finish on. Computer programming. It's a work in progress. And it never ends, which is maybe why we're all still here. So I'd like to thank Mairead, Siobhan and Eamonn for having a chat about computer programming. We're going to make this machine podcast a fortnightly release for now. We don't have any social media set up. It's available on all the major podcasting platforms, but we'll sort all that out later. So thanks very much, lads.
Thanks, Rob.
Thank you. Thanks for having us.
Good.